So in this video, we're going to focus on retention factor, or what used to be called retardation factors, in TLC and HPTLC plate theory. So retention factors is going to be a value that we can assign to these spots that we want to report, that we want to discuss, that we want to list in some type of table maybe for a reviewer or to represent our data in some form or fashion. So retardation factors were used. That's what RF used to stand for. They got weirded out with the term retardation and they just didn't like to use it. So now what they call it is retention factor. So the retention factor, that R is retention, and retention means to hold back. And you know, there's actually people now that are just really weirded out with the word retention. They don't want us to use the word retention for some good awful reason. There's now discussion on, do we still need to call this RFs? Do we still need to refer to these as retention factors because we're retaining or we're holding back the spots? We don't want to hold back the spots. We want the spots to be supported. We want the spots to do well in their life. Well, okay, that's not really what we've ever really referred to when we used even the word retardation factors. It was this idea that we were holding things back and it was slowing down. And I'm sorry that that offends somebody, but we weren't even using that for that purpose anyway. But now, as of today, it's still called retention factor, or RF. So normally, again, these spots are going to travel up. These bands are going to travel up. This dotted line here is in the image is basically the origin. This is the starting spot. So this is where I have placed my sample in the very beginning. And then as the development has happened, as the plate has now worked with the gas phase, the liquid phase, aka mobile phase, the stationary phase that's placed on the plate, as all of these things have come together and as my sample begins to travel up and up and up, we see some distance that is traveled. We see a migration rate that has traveled. All right, so here is the starting point, and as I go up and up and up and up and up and up and up, I see a circle that stops there, and that circle is probably a component, and that component I want to measure. How far did that go up? So that is my spot distance, or my component distance. That is what that represents. A lot of times these are going to be measured in centimeters or in millimeters. It does not matter as long as the unit is the same. That's the beauty of the equation, because whatever you are measuring in, your RF is going to be calculated the appropriate way. If you measured it in centimeters, great. If you measured it in millimeters, not a problem. So for instance, if my centimeters was 2 centimeters up, that is 20 millimeters up the plate. That is okay. That is not a problem. The math will make it work in the end. Trust me, it does. All right, so I would measure the spot distance there. Next, I've got another spot over here, right? So here's kind of the spot where it started down here at the bottom at the dashed line, and then it goes up, 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 and then around there, that is a spot. That is the spot migration distance. So that means that spot is where my sample is going to be migrated to. So I need to be able to calculate that distance. So how far did that go up? Let me bring out a ruler. Let me bring out something that will measure that for me. Maybe that's a software platform that will do it. If so, great. But I need that retardation factor or retention factor to be calculated. And the way that we do that, one of the most important pieces is how far did the spot travel. Okay. Next up, I got a third one. It's right here. So up, 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 up. There we go. There's a third spot. So that I can again measure the distance in centimeters or millimeters and be able to be ready to do a calculation with that shortly after. All right. Next up is the idea of the mobile phase distance, right? So for instance, I can go into the lab and I can develop these, and I can let my mobile phase go like halfway up the plate. Somebody else can go in and develop them, and their mobile phase will go 3/4 of the way up the plate because they had more time to waste. And then other people, they will spot these samples, and they will only allow it to go 1/4 up the plate. So not even half. So they're going to stop it way early because they're going to try to rush through it, and they're going to think that that's okay, and they'll still get data. That's not how any of this works, and that will drastically affect your measurements. So that mobile phase level is very, very important. And that mobile phase level is where the height is concerning where the mobile phase has reached. So here's the dotted line. That's where everything started. So I'm going to also use that as the start line for my mobile phase. And then I'm going to go up, 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 up. And then right up there is our penciled line, not a pen, shame, shame. There is my pencil line that I have marked all the way across the plate. When I go all the way across the plate, okay, I'm making sure that I'm tracking and that I'm marking the appropriate level of mobile phase all the way across, because we've already discussed that that could be different. It might not be a straight line totally across. So I need that distance. I need how far did that mobile phase reach up to the top of the plate. And again, that's going to be in centimeter, or is that going to be in millimeter? That's up to you. You just need to make sure that the spot distance and the mobile phase distance is measured in the same unit. When you do that, the spot distance will be on the top and the mobile phase distance will be on the bottom. And you take those two values and you divide them. And that is how we calculate a RF value. That's what goes on. That's how we report these numbers. And the RF values are going to help us identify the unknowns that might be in our sample, as long as we're comparing it to the knowns that were also ran, get this, on the same plate. We've already talked about that too. We've already discussed that samples and standards have to be ran on the same plate. Even though we use instrumentation, it has to be done on the same plate. The developing conditions are different. Humidity values, temperature values, they might not be identical. And if they are not, or if my composition is slightly off, then it's going to affect the way that these things separate and travel up the plate. And that means there are different RFs that will appear from plate to plate, even on the same standard stuff that we are analyzing and that we're doing. Now, we hope not, but that is part of using instrumentation. We can actually make this more reproducible, but those changes can still happen. So, rule of thumb, again, standards and samples on the same plate. You need those, right? You can't do standards on one and then samples on the other one and expect that those RFs are going to perfectly match. They might get close, but they will not probably perfectly match at all. All right, so when you calculate these RFs, the RFs will typically be below the value of 1. It will be below because the spot should not travel further than the mobile phase. That makes sense, right? So the mobile phase should travel the fastest. It should be the highest one up the plate. It should have the largest number. Therefore, if I divide anything by a number that is bigger, I'm going to get a value less than 1. That's just the way that this happens. So RFs are going to be lower than 1. The problem, though, is that in real world type of scenarios, sometimes people do not like RFs that are like 0.98. And the reason is because that decimal number is there. And decibels maybe mean something or maybe nothing at all, depending on the country that I'm working in. So there is a chance that someone will ask you to correct for the RF value. And when they do this, they are talking about multiplying by 100. So they will take the 0.98, multiply by 100, and get a 98 instead. If they have a 0.37, they will multiply by 100, and they will get 37 instead. This does away with the decimals. That way there's no confusion depending on what country I'm working in as far as laboratory data is concerned. And you know, sometimes people don't even use decimals, they use commas. So what does that even mean? So we've got to somehow streamline this in a way that makes sense for everyone. And this additional step with our RF values of multiplying by 100 is somewhat common practice. If I do this, what they very often will report is a little h that is in front. And that h is going to be a modified version of RF, and that is our RF times 100. So if you were in the forensic chemistry class, there is a chance that we analyzed maybe like a sample of cocaine to see if it was actually matching or not. If we did that on HPTLC, well, okay, there is a UNODC document that we had to follow. That UNODC document was all about RFs, and it gave me tables, and it was like, this is where cocaine should be if this is the mobile phase and this is the stationary phase that you chose. Okay, good, thank you. But they were all whole numbers. And the reason they were whole numbers is because United Nations, they're not going to take the risk, they're not going to take the gamble of what a decimal point means. So they actually report the RF times 100, so that way it's reporting RFs in terms of whole numbers. And people now know kind of what to do based on how they want to report the data in. All right. So this is kind of how the instrumentation will do its job. It will calculate, for instance, an RF straight out RF. It's up to you to move that decimal over twice. And again, United Nations, UNODC, other regulatory agencies like the USPNF, they might require you to do it as well. And that is the intention of why that is happening. All right. So that is how we calculate RF, aka retention factor, on a TLC plate. You probably have had to do this already with some of our labs. Maybe you didn't multiply by 100, but you were able to measure some spot distances and some mobile phase distances on where things traveled and how they did that. And now we get to formally kind of discuss and talk about it, of course. Next up, something else that we can talk about with spot distances and migrations is the idea of efficiency. So efficiency, back in the intro to chromatography lecture, meant something, and efficiency was capitalized with an N, and efficiency is going to still be capitalized with an N here as well. We said that efficiency was the concept of theoretical plates, and the number of theoretical plates, the more pages I had in the cartoon flip book, the smoother that cartoon was going to be. Absolutely, that is what this is all about. So on the same things happening on the plate, the more pages, the more separation steps we have on the plate, the smoother the separation, and the better the separation is going to be. So we can calculate efficiency on a TLC plate just like we can calculate an efficiency inside of a column. Whether it's a handmade column or whether it's a manufactured column on an HPLC instrument or something similar like an IC system, we can do this. It is not an ordeal. It's just going to be a little bit different as far as an equation goes. So to calculate the efficiency or the number of plates on or theoretical plates on a plate of a TLC plate, we're going to take X and we're going to square it and we're going to divide by W. That is also going to be squared. The X is the migration distance. So this is of the sample. So in other words, this is the spot distance here. I'm going to take the spot distance and I'm going to square it. And then I'm going to divide it by the width of the spot. And the width of the spot is basically the diameter. And again, I want to make sure that these are the same units. So if I'm measuring this in centimeters, I'm going to measure the diameter in centimeters. If I'm measuring this in millimeters, I'm going to be measuring that one in millimeters. I've got to make sure that they are the same or this is not going to work, folks. So once I do this, I'm going to square it. And when I square each one of these, I'll divide it. And whatever number that is how efficient the plate is for those particular compounds when it comes to separation. The idea here is that I want my spot to be really tiny. And the smaller that spot is, then that's actually great news for me. Because that number, when I plug it into this calculation, is going to give me a large N value. And that large N value is number of theoretical plates, and that's a smoother cartoon and a smoother separation. I do not want my spots to be super large and super blobby. Those diameters are going to be quite large. Those numbers, when they get filled in, when they go into these calculations, that's bad news bears, folks. I do not want that to happen. Efficiency also, by definition, it's talking about the migration distance of the compound, which is really in terms of the center. That is really how this equation is going to be termed. So when we talk about migration distance here, if we are talking about it in terms of efficiency, I should really be trying to figure out the center of that spot. And the center of that spot is where I'm going to make the measurement for my spot distance. And then the diameter of that spot is how wide, all the way across. How wide is it? We hope it's universal. We hope it's circular. We hope it's not an elliptical type of situation. We hope it's not like an arrow. We hope it's not curvy. We hope that this thing is really, truly a spot. So that is N, which is efficiency. That's how we calculate that value. As far as bands go, we can do that as well. Instead of spot distance, we're talking about band distance. And band distance is actually a little bit better because, again, it is not a wide spot. I don't have to worry about the center. It should be lines or very thin bars that are showing up on the TLC plate image. So I'm going to go to kind of the center, and there is often no question on where that's going to be. I'm going to click on that line because that line is going to be very thin, very narrow, we hope, but I can still see it extremely well. So we can calculate it that way as well. Not a problem, not an issue, but it's how wide is the band, so in AKA how thick. How thick is the band? Not width as in this way, it's the width as in how thick is it, and then we have a band migration distance, all right? Next up is height equivalent to a theoretical plate. We talked about this as well, that's HETP. Height equivalent to a theoretical plate is how thick are the pieces of paper in the cartoon. So how many can we cram in? The shorter the height is, the more plates that will fit on that master TLC plate. Again, the thinner the individual separation steps are, the more slivers we can put into a column. So the same concept, the same idea happens here as well. So HETP can be calculated, and the way to do that on a TLC plate is you take X, and X, again, is the migration distance of the spot. And again, this is centimeters or in millimeters, whatever you want to put it in. And then N is the efficiency, and the efficiency is coming from the equation up above. So once we have the number of individual separation steps, we can take the spot distance, we can divide by the number of individual steps that it has experienced to get to that point, and that will tell me the height of each one of these theoretical plates that are on the surface of that TLC plate for me. Again, it's all about silica. It's all about the stationary phase. It's just a way to describe how things are separating, and the more individual steps that it encounters, the more baby steps that it sees, the better the separation is going to be. All right. In the next video, we're going to keep talking about equations, and in the next one, we're going to talk about resolution. So how do we calculate resolution on a HPTLC plate? We'll come back and you'll find out.